Okay, so we're back to continue our look at real eigenvalues and what kind of effect they have on the straight line solutions on the phase plane. So for this next example, we have another similar situation where we have um, a matrix equation that we're going to be able to solve using eigenvalue eigenvector method. And again, we're going to cheat and use Maple. So again, I encourage you, figure out what's going on with Maple. Figure out your lambda and your v for number 1 and number 2 on that. But I do want to point out something that's kind of worth noting. This right here actually represents a partially decoupled system. If you notice, if you turn this into in terms of x of t and y of t, this would be dx dt, top equation would be 3x plus 2y, and the bottom equation would be dy dt equals 0x minus 2y. And so that one you could solve using our separation of variables technique and then do substitution into the other one. So there is actually a way to solve this using prior techniques, but we don't need that because thanks to Maple, we know lambda 1 is equal to 3, lambda 2 is equal to negative 2, and the corresponding eigenvectors, v1 is 1, 0, which is basically pointing in the x-axis direction, and v2 is, well, the way it pops out in Maple, at least it did for me, was this, negative 2/5, 1. Now there are alternative ways that that might show up. Because remember, writing an eigenvector, it can be written many different ways. It's just really about the direction that it's pointing. So now if we write our general solution, all we need to do is kind of put everything together. Y of t equals k1 times e to the 3t times its eigenvector plus k2 times e to the minus 2t times its eigenvector. And as before, you can see the two straight line solutions. So there's straight line solution number 1, and that follows the x-axis, so y equals 0, right? And right here is our straight line solution number 2, and that follows the line. If you plug in 1 for y, out comes negative 2/5 x, or another way of saying it is if you plug in 1 for x, out pops negative 5/2, whatever that is. So you can tell the direction that these two straight line solutions are going just by looking at it. And of course that means we could also rewrite this as an x of t, y of t pair of parametrics. And the top one is going to be k1 e to the 3t plus, or I should say, minus 2/5. Got to look ahead a little bit. Minus 2/5 k2 e to the minus 2t. And then down here, something interesting happens. This just kind of goes away. There's no first term for the solution for y of t, and all that it has is k2 e to the minus 2t. And so that means, if you pay attention to the x and the y, that as t approaches infinity, the x of t is going to blow up and get bigger and bigger and bigger and bigger and bigger. Because while this is decaying, this is not. So our x of t will approach infinity. And y of t will, interestingly enough, approach 0 as t gets bigger and bigger and bigger. So what the heck does that mean? where you have in the x direction, everything's kind of going taken off away from the origin, and in the y direction, everything's headed towards the origin. What does that mean? Well, that's what the next page is for. So if we take a look at the next page, we can actually see what our two our x of t and our y of t look like. I'm going to kind of move this up so we can see it a little bit better and get a sense of which is which. And again, we're going to use the trick of paying attention to our initial conditions. And so initial conditions, assuming k1 and k2 are just 1, if we kind of scoot things up a little bit and say, well, down here, this is when t equals 0 and the output is -1. And the only way that's going to happen is if you have your x of t situation going on. So that's got to be your x of t down here, because this is saying x of 0 is equal to -1. And so this must be our x of t curve. And of course, the guy in green over here, that's just constantly exponential decay, and that is our y of t curve. And if you wanted to see where it crosses the axis, well, it depends on where you're setting those values, that k2 value. So for us, what we're going to do is take a look at our phase portrait and say, okay, so we know that we have two straight line solutions. One of them followed the x-axis, and we called that one straight line solution number 1. And that's where lambda 1 was equal to 3. And you'll notice that all the arrows along that line are kind of pointing away from the origin. So I'm just going to kind of add little reminder arrows here, because everything along that straight line solution is running away from the origin, right? But for this other one, the straight line solution number 2 right here, you can see that everything is kind of headed towards the origin along that straight line solution. You know, even as it gets closer to the origin, it's still trying to stay on that straight line solution. Anything that's not immediately on the straight line solution is going to kind of hover close to it, and then it kind of gets pulled away by that other one. But because we can take a look at the size, the relative size of their eigenvalues, this one had an eigenvalue of -2, we can tell that this guy is going to be more influential on the phase plane than this guy is. And so that's why if you kind of go out in the middle of nowhere and you kind of take a look and you say, what's going on? Which one of these is having more of an impact? It's kind of headed more in the horizontal direction than it is in the vertical direction, because straight line solution number 1 is more of an influence. And at the bottom of the page down here, you can see that if the eigenvalues have opposite signs, so in this case, one is positive, the other is negative, then the origin is, well, what would it be? Towards along one of the straight line solutions and away along the other. And in order to really get a good sense of what's going on here, you really have to play around with the DE plot 3D. And so I encourage you to take a second and do that. And when you take a look at this with the solution curves, with initial conditions in the DE plot 3D, you see that you have, essentially it's heading down this way towards the origin and then bending away along this. And so what you have, if you remember from Calc 3, is a saddle point. It's what we call a Pringles chip, right? And so this saddle point is a very unstable equilibrium solution. It's stable in the sense that along this direction, things want to head to the origin, but as soon as they get close, if they're not right on that straight line solution, then they're just going to kind of slide off and zoom along the other straight line solution. So we've seen 3 different circumstances where we have both are positive, both are negative, and both are different signs. So the last little bit for this section, is about kind of classifying and making sense of what's going on. So the very last page here that we're going to kind of do in this video is just a quick chart to help keep straight all the bits and pieces that we're picking up along the way. And so you'll notice on this this page it says if lambda 1 and lambda 2 are related like this. If lambda 1 is less than 0 but lambda 2 is greater than 0, that means lambda 1 is negative and lambda 2 is positive. That's literally the definition of negative and positive. Then that means you have exactly what we just saw, which is a saddle point. And that means that all solutions, everywhere on the phase plane, thinking back to the previous example, all solutions are going to move toward the origin. Origin, there we go, origin, I can spell. Along the straight line solution number 1, because it's negative, direction. But away from the origin along the straight line solution number 2 direction, because that one's positive. And so kind of putting those together. And the key here, and I'll kind of add this in a slightly different font color to make it clear, that since we don't really know anything about the size of lambda 1 and lambda 2, we don't know which one is bigger, but we could say the larger magnitude, lambda, is more influential. On the plane. Similarly, we can take a look at what happens when we have lambda 1 and lambda 2 are both less than 0, but in a particular order. That means that they're both negative, but lambda 1, because it's more negative, must be a larger magnitude than lambda 2. That's kind of the definition of being more negative or more positive, means it's a higher magnitude. And in this case, if both of them are negative, then that means the origin is going to be a sink. That means everything heads towards the origin. And so all solutions move toward the origin. And because we know that lambda 1 is larger magnitude, the straight line solution associated with number 1 will be more influential. On the phase plane. And then last but not least, what happens if you have the other situation, which is both of them are positive, but one is definitely bigger than the other. And so that last possibility is telling us that both are positive, but that the magnitude of lambda 2 is greater than the magnitude of lambda 1, which is good. You know, finally, lambda 1 finally loses out here. That means that you have both positive, so you have a source at the origin. And that tells you that all the solutions will move toward the origin. And the straight line solution number 2 will be more influential on the phase plane. Phase, I don't know where that E turned into a P, but on the phase plane. And so down at the bottom, there's just kind of a definite classification. Sinks are called stable since solutions revert back to the origin, and sources and saddles are technically unstable for the opposite reason. So when somebody talks about a stable equilibrium point, they're really talking about a sink. But if they're talking about something that's unstable, they could be talking about a situation that's just a pure source, or maybe it's a saddle. And so that's it for this video. In the next video, we'll finish up the last example for 3.3.